Good morning, ladies and gentlemen. May I have your attention, please? Thank you. So we're back at it. We've got a regular Bellwork today. We're going to take the first part of today's class period to review related rates. I've gone back and forth. How do we best use our final class periods together? And in the past, I've devoted that to area volume review. This year, we shifted the area volume review back to before you took the practice test because that seems to always show up on free response. Related rates is something that has shown up on our multiple choice, but not too much on the free response. And so I'm wondering, this might be the year where it makes a comeback and shows up on free response. So we'll see. All right, so let's go ahead and differentiate term by term. Remember, implicit differentiation is a relation where we've got x's and y's mixed together on the same side of the equation. When we differentiate this with respect to x, every time we use the derivative rule on a y term, it's going to spit out a dy dx, or a y prime for short. And so we're going to differentiate both sides here to find dy dx. That is the first derivative of y with respect to x. We'll simply go term by term and utilize, bless you, a power rule. So the derivative of x squared is 2x minus 3. And I'm going to go ahead and use a product rule, right? X and y are both variables and y depends on x. And so I'm going to break up that x times y as a product. The derivative of a product of two functions is the derivative of the first times the second plus the first times the derivative of the second. What's the derivative of y with respect to x? Well, there's my dy dx, my y prime, if you wanted to put. Right, there's my dy dx or my y prime. And then still term by term plus the derivative of y squared. Power rule. It's just that my derivative of the base spits out a times dy dx. So let's try that. Ready? The derivative of y squared is exponent times the base raised to 1 less times the derivative of the base, and there's my dy dx or y prime, right? Equals, and then don't make this mistake, don't leave this 8, right? You're differentiating both sides with respect to x, so the derivative of 8 is 0. Now what did we want? We wanted dy dx, and so we're going to go ahead and solve for dy dx or y prime. In order to do that, we can get rid of the parentheses by distributing minus 3y minus 3x dy dx plus 2y dy dx equals 0. All right, before we solve, I need to go ahead and do a check with the class. Raise your hand if you had your derivatives right. You spit out your dy dx's. Hey, that's good news. So how in the world do we isolate a single dy dx then when we've got multiples? Well, we'll utilize that factoring technique. We'll go ahead and add or subtract, get all the dy dx terms on one side, everything else on the other, and then factor out a dy dx so we have a single dy dx, and then we can solve through division. So it looks to me like we want to keep this 2y dy dx. We're going to want to keep this negative 3x dy dx. All on the left. On the right, I'm going to go ahead and add over that 3y. I'm going to subtract over the 2x. And now we can go ahead and factor first or fail, right? We want this dy dx, so we'll factor out a single dy dx in a reverse distributed property problem, leaving me with quantity 2y minus 3x equals, and then still chilling, 3y minus 2x. And finally, we can solve by division, right? We can just divide now both sides to get my dy dx alone. So we get dy dx equals, and we'll go ahead and take quantity 3y minus 2x all over 2y minus 3x. What do we do with the x's and the y's? So raise your hand if you got that. Anybody else get this? You got it with the no? So did I miss the x and the y's here? So they flip-flopped? We're okay. Good? Awesome. Great. So what in the world does implicit differentiation have to do with related rates? Well, just like we differentiated this y term with respect to x, and it spit out a dy dx, the times the derivative of the base, so too, when we differentiate quantities in a related rates problem with respect to time, right, it'll spit out a times the derivative of the base. It'll spit out a dA dt, or a dr dt, bless you, or a dy dt, or a dz dt, the derivative with respect to time. And that's what related rates is all about. So to warm up now for some application problems, let's go ahead and differentiate, right, these common geometric formulas, but with respect to time. Now with respect to r, right, if we were differentiating with respect to r, we get a prime equals 2 pi r. Well, that's not what we're doing. We're differentiating the quantities that are related here in a related rates problem with respect to time. So we'll use that Leibniz notation and spit out a dAdt every time we differentiate an A term with respect to time, or a drdt. So here we go. We want to solve for drdt. We'll take the derivative of both sides. I know the derivative of area with respect to time would be dAdt equals, I'd go ahead and use the power rule. The derivative of pi r squared is going to be constant multiplier pi, and then times power rule. So we'll have exponent times the base raised to 1 less, and then times the derivative of the base. There's my drdt. So solving, it looks to me like we'll get divide over one fell swoop. This one's not too bad. Looks like I get dAdt all over 2 pi r. Awesome. Let's go ahead and differentiate both sides with respect to time. Differentiate both sides with respect to time. So utilizing Leibniz notation, what will the derivative of v be with respect to time? Joel?
4 pi r squared.
You're ahead of me, sorry. Left hand side, I just wanted the Leibniz notation.
Oh, just dv dt.
Absolutely, now keep going right side.
4 pi r squared times dv.
Beautiful, thank you, Joel, that's perfect. So it looks to me like this one will utilize the power rule as well. Our constant multiplier, 4/3, cancels out with my exponent multiplier from the power rule. I get 4. And then finishing this out, it looks like we get, again, a dv dt all over 4 pi r squared. No pi r round. Oh gosh, so 2000 late. Gosh, I missed it this year, didn't we? We didn't even have a pi on Pi Day. And now it's past March, April, May. It's May. Wow. All right, so let's go ahead and throw in something. These are pretty easy. Let's throw in something a little more complicated. So this actually showed up a couple years back. The interesting thing about this formula is that the right-hand side includes more than one variable, each of which will be differentiated with respect to time. So we have to be very careful with our differentiation here. The derivative of this must be v equals pi r squared h, so volume again, and pi r squared h. So the pi r squared must be base area of a right circular cylinder multiplied by height will give me volume. Let's do it. So on the left, dv dt. On the right, it looks like we have a product. That means we'll have to use the product rule to differentiate that. So I'm going to go ahead and break this up into two functions. I'll do pi r squared as one function, and I'll do the second function as h. Normally I would pull the pi out front, but this actually showed up on a free response in the scoring guidelines. They went ahead and just broke it up this way. So to make that match as you come across that, maybe in your preparations, I'll go ahead and call the first function blue pi r squared. Here we go. The derivative of a product of two functions is the derivative of the first what? Well, we've got exponent times the base raised to 1 less times the derivative of the base. We have to include a drdt every time we differentiate an r term with respect to time. The derivative of the first times the second plus the first times the derivative of the second. What's the derivative of the second with respect to time? Grace? Absolutely. And so that's where our unknown rate's going to be, right? There's our dHdt, which means that we've got a little bit of work to isolate that. So it looks like we'll do a subtraction to isolate the term that includes my unknown rate, and then division to finish it out. So it looks like a two-stepper. We've got our dV dt minus, there you go, minus 2 pi r dr dt h equals pi r squared dr h dt. Ooh, dh dt. It's like alphabet soup up here. You never know what you're going to get. Is it mom or wow? Just spin the bowl. And finish it out like you haven't. Like you haven't done that before, Riley. I'm so sure. I squared. So dv dt minus 2 pi r dr dt h all over pi r squared. Is that going to do it? All over pi r squared. I remember this year the global scoring 0 to 9 for this particular question involving related rates was something like 2.6 or whatever, you know, out of 9, 0 to 9, like everything's one. So this stumps a lot of students. Hopefully it's not going to stump you, right? If a related rates makes a resurgent on the free response, but we'll see. We'll see. All right. So, what questions do you have about our differentiating term by term? That's fine and dandy, but that's just one of the steps in our related rate strategy. So in our overall strategy, recall, for related rates, we've got a related rates problem when we have two or more related quantities, each of which are changing with respect to time. And so we start out with our classic, Phoebe and Terrence from the intersection, and Phoebe's going north and Terrence is going west. And after 2 minutes, right, how quickly is the distance in between them changing or increasing or whatever? So those are related rates questions. Those involve two or more quantities, right, that are each changing with respect to time. Read the problem carefully, write down the known rates and what you're trying to find. We draw a picture and label with the relevant quantities. If the quantity is changing, we have to use a variable. The only time we put a constant there is if it doesn't change, like the length of the ladder typically didn't change in our problem, so we could fill in that. But we had to keep x, right, that distance away from the wall to the base of the ladder. We had to put a variable there because that was changing as it slid away, and so on and so forth. We're going to write a formula that relates the quantities in question and the rates, right? The rates in those questions. We'll try to limit those variables only to things that are changing. We'll differentiate both sides with respect to time, and that's what we just did. And then we'll go ahead and solve for our unknown rate like we practiced. And then lastly, right? Lastly, we'll go ahead and plug in our moment of time information. So we're not going to do all these. We're just going to do a couple. I want to make sure that we get to our AP exam review and Dan Kennedy's top 10 list. I'll explain the crib sheet that George Luo, our very own Wanakee alumnus, created. And so let's go ahead and take a look which one we want to do. All right, I'm thinking we should do the classic ladder one because that always seems to show up, and then we'll do the water tankers, one complicated one. So everybody, let's go ahead and take a look at the second one. Skip. A ladder is 10 feet long and rests against a vertical wall. The bottom of the ladder is sliding away at a rate of 1 foot per second. How fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? Read the problem carefully, write down the known rates and what we're trying to find. So by golly, it looks to me like I've got the ladder rests against a vertical wall. My known rate would be the bottom of the ladder is sliding away at a rate of 1 foot per second. So bottom of the ladder sliding away, that would be dx dt. And would that be positive 1 or negative 1? If it was sliding away from the wall, that'd be positive 1 or negative 1? James? Positive 1. The distance x is increasing as time goes on, and so this would be positive 1 foot per second. Good. Our unknown rate, what are we trying to find? We want to find how fast is the top of the ladder sliding down the wall at the instant when the bottom of the ladder is 6 feet from the wall. So what are we going to find? We're going to find dy dt at the instant when bottom of the ladder is 6. So is that x equals or y equals? Monica?
X.
When x equals 6. Good, thank you. All right, so after we've drawn a picture and labeled with relevant quantities, we write down our known rates and what we're trying to find. Then we have to write a relationship for my variables that are in my rates. However, I'm trying to limit my variables only to those quantities that are changing. So what else can I fill in my picture? Maggie?
The length of the ladder,
And how long is the ladder?
10 feet.
10 feet. So that'll limit our variables because we won't have to use a third variable like z for our hypothesis. Good, thank you. All right, let's go ahead and do it. So what relationship is this between x and y and 10? Michael?
X squared plus y squared equals x squared.
Awesome. Our favorite Pythagorean theorem back from middle school, 10 squared, right? 10 squared, x squared plus y squared equals z squared. Good. And now we'll go ahead and differentiate both sides with respect to time. So I've got 2x dx dt. Every time we differentiate a variable with respect to time, it spits out a dx dt, dA dt, dr dt plus 2y dy dt equals 200. 2 times, no, comma baby. This would be 0. The derivative of a constant is 0. So don't let that 10 squared fool you. That's not power rule. Now what did we want to find? We wanted to find dy dt. So I like to isolate first, plug in last. That way we don't miss anybody. We're going to go ahead and solve for the dy dt. And we'll do that by subtracting over our 2x dx dt. Dividing by our 2y, so I'm going to divide out the 2's already. I get negative x dx dt all over y, and then we'll plug in last. So at the instant when x equals 6, y must equal 6, 8, 10, 3, 4, 5, so 6, 8, 10. So we could do a Pythagorean theorem again for the moment in time value to get y, and 100 squared minus 36 is 64. The square root of 64 is 8. So at that instant, when x equals 6, y equals 8, which means we can get our final answer. We get negative 1, 2, 3 fourths. 3 fourths. What would a label on our dy dt be? What would a label on that be? Riley E? Feet per second. Uh-oh. We got a negative. Did I mess up? Do we have a negative here, Tyler?
Yeah, it's sliding down.
Oh yes, the ladder is sliding down the wall, so that quantity y would be negative, right? It's changing with respect to time, and that value y is decreasing as the ladder slides down the wall. Therefore, the negative answer makes sense. Now when it's asking how fast, right, we could then say, oh, well, if that's speed, then it's always positive. However, dy dt itself is negative. And so depending upon what the question is asked or how it's wording, yes, this would be a positive 3/4 feet per second for speed, but dy dt is negative. Either one is fine. The point of this was to remind you about how each term gets a rate spit out. Michael?
So like if we know the instance and like why don't we just put it in? I get like there'd be a 0 value, but why wouldn't you do that?
That's a great question. So if we know that the instant when x equals 6, we could figure out what y is. Y equals 8, right? Why can't we plug that stuff in? Because then we lose our variables, right, that are changing with respect to time, and we would no longer have a dy dt. And that's what we're trying to find. And so we never want to plug in our moment in time information until the very end after we've differentiated and got our relates involved. So we'll go ahead and differentiate first, isolate our unknown rate, and then plug in our moment in time values last. That way we won't lose any changing quantities. Awesome? Great. Let's do one tricky one. A water tank has the shape of an inverted cone with a base radius of 2 meters and a height of 4 meters. If the water is being pumped into the tank at a rate of 2 cubic meters a minute, find the rate at which the water level is rising when the water is 3 meters deep. I'm having flashbacks, and not in a good way, right? Cold sweats, beads, right? Beads of sweat form on my brow. I remember something like this. This is going to have lots of variables involved. So let's go ahead and consider this water tank, the shape of an inverted cone. We were to draw that. We're thinking ice cream cone, not geometry sketch pad cone. So here we go. I'm getting hungry. Is it too early in the day to be hungry? I'm hungry all the time. Please. Forget about it. Oh, water's being pumped into the tank at a rate of 2 cubic meters per minute. Find the rate at which the water level is rising when the water is 3 meters deep. Oh gosh. So let's see if we can't write down our known rates, unknown rates, and label our picture with some variable quantities and hopefully some constants as well. So our known rate is the pumping rate. It's been pumped into the tank at a rate of 2 cubic meters per minute. So what lightness notation makes most sense to use for that? Right? Lightness notation should I use for that? Kobe?
dV
dV dt for the change in volume. Bless you, I'm down. So let's go ahead and do dV dt, and that is a positive 2 cubic meters per minute. Awesome. And I'm trying to find, what rate am I trying to find? Looks like we're trying to find the rate at which the water level is rising when the water is 2 meters deep. So it looks like we need some more variables here. We need the water level. I'll call H for height of the water. Then we'd be trying to find HTT at the instant when the water is 3 meters deep, so that would be when H equals 3. All right. Well, we're almost done. What else do we need? We need a formula that relates the variables in my rates. And so I need a formula that relates the V's and the H's. And as I look at this picture, I'm getting right circular cone, so I'm thinking we need R's in here too. So it looks like we need an R for the radius of my water, and a big R for the radius of the cone. Or does the radius of the cone ever change? No, what's the radius of the cone? The tank cone. So we can fill that in as a constant because the tank cone is never going to change. Just the water cone is going to change. So 2 meters. And the tank height, oh, now we're talking. That doesn't change. That's always 4 meters. I think we've got it. So now we can go ahead and write a formula that relates the quantities, right, that are changing. In question, the V's and the H's, and we'll go ahead and use our formula for the volume V of a right circular cone, inverted or otherwise, is still given by, what, 1/3 pi r squared h. This is fun. It's like a trip down memory lane. We've got geometry. We already had middle school for Pythagorean theorem. You know what I'm saying? 1/3 pi r squared h. And if there's any way we could limit the variables in question, that would be great. Well, as we go and consider our picture, and I've tried to draw this so we could see what relationship do we have between the tank, right? The tank and the water cone. Well, they're exactly the same shape, different sizes, but same shape. What kind of figures are same shape but different size? What's that called? Similar, right? And if they're similar, then they're proportional. And so we can write a relationship like R is to H in little cone, just like R is to H in big cone, or however any of the 6 proportion that you want to write. I'm going to say R is to H, just like 2 is to 4. That'll allow me to solve for R and plug in so that I have just a single independent variable H, the quantity in my unknown rate that I'm trying to find. So I'm going to go ahead and multiply this H over and reduce. I'm going to get R equals H over 2. Now I can rewrite this. I get V equals 1/3 pi quantity H over 2 squared times H. What? Yeah, H over 2 is my R. Another rewrite. Let's do it. H over 2 quantity squared would be H squared over 4 times H is H cubed. And the 3 on the bottom makes 12, so I'm getting pi H cubed over 12. That's not so bad, right? Are you guys getting that? Do we do that, the 4 squared? No, 2 squared is 4 times the 3 is 12. That's my horn, though. All right, finally, you can differentiate both sides with respect to time. Let's do it. So, the derivative of volume, v with respect to time, dv dt. 3 times pi over 12 times h squared times the derivative of the base, dh dt. Did we get everybody? Yes? So then 3 pi over 12 will reduce to pi over 4. We're solving for dh dt. So I get pi over 4, so 4 dv dt over pi h squared equals dh dt. Let's check that. So pi over 4, I'm going to get a 4 over pi when I isolate, dv dt on top, and then dividing over my h squared gets me an h squared on the bottom, so let's check and see how many times I messed up there. One step. You guys getting the same thing? You're getting the same thing? Yes! Isolate first, plug in last. Don't lose any changing quantity information. Here we go. 4 dv dt, that's 2, over pi. H was, the instant was 3, so pi h squared. And we're almost there, you guys. 4 times 2 is 8, and that's 9, 8 over 9 pi. What's an appropriate label for my dh dt given the context? What's an appropriate label for my dh dt? Kyle?
Like meters per minute.
Meters per minute, good. That's a changing length with respect to time, so dh dt would be meters per minute. Good. And you can always get those units by looking at your Leibniz notation. I really like the first derivative Leibniz notation, right? dh dt is going to be h units over 2 units. It's that second derivative Leibniz notation that's funky, right? That d2h dt squared, right? That's the one that doesn't make sense to me. All right. In any case, you guys killed it. We're going to get some test choice review time in a minute. I'm not going to, but Marissa and Hayden have been putting together a brief presentation about how our test W, H, S relates to test R. But first, we need our global tips for AP Calculus exam, the best top 10 list, and choice review time, all of which are on your AP Calculus final review date. So everybody find your packet that says AP exam review date. AP exam review date. Everybody find it? Awesome. Global tips, right? Things that are going to help you in general. So I'll work. Remember, the grader's not really interested in finding out the answer to the problem. The grader's interested in seeing if you know how to solve the problem. So show your work so they can see thought process, even if you don't get the answer point at the end. If you show your work and thinking, then you can earn partial credit. There's a lot of process up for grabs on the free response. Don't round partial answers. We saw this time and time again. Store them in your calculator. STO, first column, right? Eighth row down, STO. You can store those decimals so you don't compromise accuracy. Some people lost points on your unit test that you're going to get back in just a little bit because you didn't keep 3 places past the decimal in accordance with the College Board to get your answer point. We've been talking about that throughout the year. So make sure that you're storing your decimals in your calculator, and then your final calculator allowed on that free response 1 and 2. Make sure that you keep any decimal answers 3 places accurate past the decimal. Don't let points at the beginning of the problem keep you from getting points at the end. So if you can do part C without doing part A and B, do it. If you need to import an answer from part A, and we saw this actually on your practice test, you're going to make a credible attempt at part A so that you can import the possibly wrong answer into part C and still get your points. And so there's backgrading that exists on the free response questions. If your response to part C relies on a portion of part A, right, but you did part A wrong, you can still get your process points in part C, right, so long as you import your incorrect answer and use it correctly for your part C. If you use your calculator to solve an equation, write the equation first. And so, if it's asking to find the area in between the 2 curves over the interval A to B, don't just put 4.935. Show the calculus, show the integral with the calculus and the upper and lower limit, right? The calculus integral, and then go to your calculator, do math 9, and put approximately 4.395. You know what I'm saying? So you have to show the integral that you're doing. They want to see that setup. And a lot of times you see in the scoring guidelines, that setup is worth points, whether you get the right answer or not, right? You want to make sure you're showing that calculus. If you use your calculator to find a definite integral, write the integral first, just set it. All right? That's what you got to do. You got to show the calculus, show that. Whatever. Right, show that first. Bless you. And then go in, and then go and do it. Or whatever. Don't waste time erasing bad solutions if you're on the free response. If you change your mind, you can simply cross out the bad solution after you've written the good one. Crossed out work will not be graded. If you don't have anything better, leave the old one. It might be worth a point or 2. And so don't spend time, right, erasing old stuff. You don't have to. If you cross it out, then it won't be graded. Even if there's right stuff in it, once you cross it out, right, it won't be graded at all. It won't be looked at. And so if you don't have something else to replace it with, just leave it, and you might get a point or 2. Right? So you don't have to erase. Don't use your calculator for anything except graphing functions, computing numerical derivatives. What's our numerical derivatives? That's our math 8 command. So math 8. Computing definite integrals. There's our math 9, my favorite. And solving equations. And so our solving equations could be anything from second, calculate, intersect, right? We did a lot of that to find when the 2 functions are equal to one another so you can get your limits for the upper or lower limit. Or setting equal to 0 and then solving graphically by doing second, calculate, 0. Each of those would be considered solving the equation numerically. So that's definitely a proper use of your calculator. In particular, though, don't use it to find max or min points, right? You want to see the calculus, the first derivative test, the sign test. Those are the kinds of things you'll be doing to find max and mins. You're using the calculus to do that. You're not doing pre-calc style, second, calculate, maximum, right? Left bound, right bound, enter. You're not doing that. Don't use your calculator to determine concavity. Don't use it for inflection points, increasing, decreasing, domain and range. You can explore them all with your calculator, but your calculus, your solution must stand alone, right? Show how the grader, how the calculus relates to those quantities. Be sure you've answered the problem. For example, if it asks for the maximum value of a function, Yes, some of you did this on your practice test. Don't stop after finding the x value at which the maximum value occurs. You have to go and find the y coordinate, right? The maximum value of a function is a function value, a y value, not just the x value wherever it occurs. At the same time, don't waste time finding the maximum value if it just says where does it occur. Stop when you get to x because you can save yourself a couple minutes by not having to go back and find the y coordinate. So make sure you're answering the question that was asked. That'll be most efficient with your time. Be sure to express your answer in correct units if units are given. You can eliminate some incorrect answers in the multiple choice section. It's advantageous to guess even if you're not sure. Nothing's counted against you, so incorrect responses aren't counted against you. It's total number correct multiplied by the 1.2 that you did on your scoring worksheet in order to get your multiple choice portion contribution of your overall composite score. So don't leave anything blank. Wrong answers can often be eliminated by estimation or by thinking graphically, and so it's oftentimes easy to narrow it down to two, right? If you can narrow it down to two choices, then you've got a great shot at getting it right. Well, at least 50-50. You go ahead and lean against me, I'll lean right back. That way we don't have to sleep in the mud. If they ask you to justify your answer, think about what needs justification. They're asking me to say more. If you can figure out why, your chances are better at telling them what they want to hear. For example, if they ask you to justify a point of inflection, they're looking to see you realize that a sign change of the second derivative must occur. Not just the second derivative equals 0, right? In order to have a point of inflection, f double prime has to change sign at x equals c in order to have a local minimum, right? F prime has to change from negative to positive at x equals c and so on and so forth. And now, the moment you've all been waiting for. No, not that moment, Riley. Or that moment either, Riley. Or Riley. Or Riley. Or Riley. It's better than David Letterman's old school top 10 list. Even Stephen Colbert. It's better than Jimmy Fallon's Tonight Show. It's the top 10 student errors on the AP Calculus exam. This is adapted from Daniel Kennedy, longtime steering committee member for the AP Calculus exam. So I'm pretty excited about that. Oh, I can't do it because we're recording. Here we go. Number 10. F double prime of x equals 0 if and only if x comma f of x is a point of inflection. So what we're going to do is we're going to go through and we're going to fix each one of these errors, right? You're not going to be a statistic. You're not going to be one of these top 10 student errors. I know it. So what's wrong with this reasoning? F double prime equals 0 if and only if x comma f of x is a point of inflection. What's wrong with that? You can spot it. Riley E.
F double prime is the change sign.
Love it. Oh, f double prime must change sign in order for f to have a point of inflection. Absolutely. It's not enough for f double prime to equal 0. That's just a potential point of inflection x coordinate. Must change sign in order to have a point of inflection on f. F double prime must change sign. Thank you. Nice job. Number 9. F of x is a maximum or minimum if and only if f prime of x equals 0. Deja vu, like I feel like I've been here before. Deja vu, I feel like I've been here before. Kyle?
It must change signs as well.
Which must? F prime must change signs in order for f to have a relative maximum. Good job. F prime of x must change signs in order to have a relative maximum. Oh, change signs. In order to have a relative. Not like aunt or uncle, but local maximum. Even if they live out of town. Number 8. Average rate of change of f on an interval a to b, now they get a little bit trickier, is what? The average of f prime of a and f prime of b. So add up f prime of a plus f prime of b and divide by 2. So we know that's an error. That's wrong. Right? Why is that wrong? What's wrong with that, Michael?
That it's not always 2. It's a minus b. Or, yeah.
So it's, let's see, it's f at b. Let's look at this. So the average rate of change on an interval, this is great review, the average rate of change on an interval is given by graphically the slope of the secant line, algebraically the old school y sub 2 minus y sub 1 all over x sub 2 minus x sub 1 slope calculation is just in function notation f at b minus f at a all over b minus a. Yes, good. What's this picture? I've drawn it purposely to show why this cannot be correct. Right? What's the instantaneous rate of change that is f prime of a? I don't know what it is, but it sure is positive. Isn't this a positive slope? And isn't this a positive slope? And when I average those, I'm going to get a positive slope, right? And yet the average rate of change on this interval clearly is negative, right? As you move along this left to right, the function value is decreased over a to b, so this must be a negative average rate of change. And so I've drawn it so that we can see that that is not correct. That's a fallacy. Oh gosh, for all you AP litters out there, I know some of you are taking those examples coming up too. All right. All right. So number 7, volume by washers is the integral from a to b of pi r minus r squared dx. What's wrong with this? Looks good. No, Megan.
You need to separate the r's, you can't split them together.
Yes! Thank goodness! Hey, we're just 22 less statistics right here. Good job, you guys. We need pi r squared minus pi r squared. You can have the pi out front, and oftentimes you do, right? So I'm going to write the pi out front because we will often have that out front in multiple choice, but we need r squared minus r squared. It's not r minus r quantity squared. Good job, Megan. That's perfect. You down? Number 6. Separable differential equations can be solved without separating the variables. Sorry. That's an error. The only way we can solve a separable differential equation is if we can separate the variables. And we can do that through multiplication and division. We can't do that through addition or subtraction. So we must separate the variables by multiplication or division. And then integrate both sides term by term. Multiplication or division. And we've done lots of those. Hopefully you've been seeing those that have been showing up in the free response, right? There's been showing up and then solve and find a particular solution with the initial condition for like part B or part C. Make sure you separate those variables by multiplication and division before integrating both sides. Throw in a plus C on the independent variable side, and if you plug in your initial condition 0, 1, right, you almost always get at least 4 or 5 out of 6 points, even if you get the wrong equation at the end. Number 5. Omitting the constant of integration, especially in initial value problems. I just alluded to. How do we correct that? Easy. Anytime you evaluate an indefinite integral, don't forget the plus C. Right? Don't forget the plus C when you evaluate an indefinite integral. I think that deserves some quotes. Don't forget the plus C. Okay, don't forget the plus C.
Why does that do that close?
But just for fun, because then you can repeat it. Plus C. Mr. Fritz said it. But if you say it, then it'd be Sammy said it.
Yes, sir.
Yeah. Number 4. Graders will assume the correct antecedents for all pronouns used in justifications. What? This is an English class, Mr. Fritz. No, it's not. But by golly, it has a relative maximum because it switches from positive to negative at x equals c. Oh, no justification points. 0. What's wrong with that? Sounds calculus-y. Right? It has a relative maximum because it switches from positive to negative. Sorry, Sammy. I have quotes there. Can't have them. It's already quoted. So what's wrong with that? Sammy?
There's
Yeah, we don't know what it is, right? And this is not the correct justification, depending upon what that it is. And so what would we have to do to fix this one? Well, what would it be if it has a relative max? And what would it be to justify that? So f, right? F of x has a relative max. Because, and then in order to justify that, we'd have to say what? What would this have to be? F prime of x, which is from positive to negative x. There we go. So don't use it. If you find yourself writing it in the justification, stop, right? Erase it or cross it out and put a label, a noun, a subject, a specific. Number 3, if the correct answer came from your calculator, the grader will assume your setup was correct. Not necessarily, right? So make sure you're showing your setup, show the calculus. That's typically an integral, right? Show the calculus setup before you go to your math 8 or math 9. Number 2, now we're to the biggies. Universal logarithmic anti-differentiation. What? This is a top 10 student error. Got the number 2 spot. So what's wrong with the integral of 1 over f of x dx is the natural log of absolute value f of x closed bars plus c? Right? Isn't that when they remember their bars? Megan?
Well, if you get anything with like x squared, anything over x to the first, it's not, that's a lot.
Yep, absolutely, right? Just because there's a fraction doesn't mean it's a natural log antiderivative. We've got all kinds of fractions, right, whose antiderivatives are not natural log rules. Only when we have a quantity on the bottom to the first power is it a candidate for natural log, and then it only will be natural log if the derivative of that quantity exists. And so that's the key difference between something like this . Only one of these is a natural log rule. Okay, only one of these is a natural log rule. Who spots it? The first one's the only natural log rule. What would the second one be for an antiderivative rule? What would this be? Colin?
Would it be just like 1 over 1?
For antiderivative? Think derivative. Okay, what differentiates to 1 over 1 plus the input squared? What's that? What's the second one come from? Inverse tangent. Inverse tangent. Right? Inverse tangent. What would the third one be? That's what you're thinking. What would the third one be? There's power rule. Right? So it'll be negative 1 over, right? Negative 1 over 1 plus y. Basically the opposite of that. All right, guys. And now, the number 1 AP calculus in there, the derivative of f of y equals f prime of y. Isn't that what we learned all year? The derivative? Is that prime? Right? What's wrong? What possibly is wrong with this? What is this missing? Gosh, it looks good. Riley?
It's not in respect to y.
It's with respect to, so we'd have to include a
Y prime.
darn tootin'. The derivative with respect to x of f of y is f prime of y times y prime or dy dx. Absolutely. Times the derivative of the base. There's our chain rule. You guys are awesome. You guys are awesome. Wow, we've got a wealth of resources available at our disposal. Please note, the test W was the 2012 College Board released International Practice Exam. So you've got test W, you've got test H, that was from 2013, test S, 2014. All of these, right, are full-length stuff that you've got all back. Free response, 13, you are going to pass in, and I'm going to pass back. 14, you kept from your Bellwork. 15, you just got last class, it'll be due next class. Those are the most recent ones. 2011 is extra practice, it's not due, but you can go and check out the link there on our Moodle site. 2003 multiple choice part A and part B, this was the actual exam. They're very stingy with their actual exam releases, so this is hyperlinked on Moodle. You can check this out if you want more multiple choice practice, but you guys have been doing well. And then area and volume review, that's what we did right before we started the time testing, and that's always a good thing to look over, because what have you noticed from the free response questions? Well, one of those free response is always an area volume question, right? That's kind of a go-to thing. One of those free response questions is always some sort of area volume question. Awesome. So you got all those things at your disposal. I'm going to go ahead and share your unit test scores from test R, right? And then Hayden and Marissa will have their very short presentation involving the nomenclature for our practice test prep over the last 2.5 weeks. So we've got that. I'm going to go ahead and stop the recording and then get your OTL collection taken care of.